The last of the single-stage MOSFET amplifier configurations that we shall study is what is known as the common drain. This is obtained by establishing a signal ground at the drain and using it as a terminal common to the input port between gate and drain and the output port between source and drain. But we see from the circuit that drain is in fact connected to VDD. So how is the signal ground established here? Notice that the voltage across an ideal constant DC voltage source such as VDD does not change, and so there will always be a zero voltage signal across a constant DC voltage source. Using this fact, in the small signal analysis, we short the voltage sources. Therefore, we will establish a signal ground at the drain. Now, in order to carry out the small signal analysis, we need to construct the small signal equivalent circuit. So, any guesses for which model should we use, the T model or the hybrid pi model? Note it down with you and let me make the small signal equivalent circuit. Yes, we employ the T model. Why? Because RL is in effect connected in series with the source terminal of the transistor. Therefore, the T model is more convenient to use. However, notice that RL is not in series with 1/GM. Also notice that we have included R0 again. Why? Because it could not be ignored. Its value is significant in this analysis. So we start off and notice that Rin equals Rg. We can write the equation for Vi and we select Rg to be much larger than the internal resistance R sig. So we get Vi is approximately equal to V sig. Now take a look at the resistance R0. It is in parallel with RL. Why? Because this terminal here and the ground are two terminals that are common to both R0 and RL. Also notice that R0 and RL are in series with 1/GM, not individually but together as an effective resistance. The signal Vi appears across the entire effective resistance. The voltage Vi appears entirely across the series combination of 1/GM with the parallel combination of R0 and RL. Let me write this down. Get it? Now V0 is not just the voltage across RL. Remember that when we have resistances in parallel, the voltage across them is the same. So V0 is also across R0. Now using this we can easily obtain the voltage gain. And for this circuit, we introduce another quantity, the open circuit voltage gain, AV0. This is when we put RL to infinity or we remove the load. So, the open circuit voltage gain would be R0 divided by R0 plus 1/GM. Now, R0 is usually very large and much larger than 1/GM. This means AV0 is almost unity. This means the voltage at the source, that is V0, follows the voltage at the gate, that is Vi. And this is why this circuit is known as source follower, a very popular term. Now the overall voltage gain can also be written, and this also approaches unity for Rg much larger than R sig, R0 much larger than 1/GM, and R0 also much larger than RL. The final quantity that we have to calculate, that is Rout, we short V sig in the small signal equivalent circuit and look back into the source. Now we see between the source and ground here a parallel combination of 1/GM with R0. And as we know, R0 is much larger than 1/GM, so Rout comes out to be 1/GM, and it is a very low value. Now, the source follower features a very high input resistance, a low output resistance, and a voltage gain that is less than but close to unity. It finds application in situations in which we need to connect a voltage signal source that is providing a signal of reasonable magnitude but has a very high internal resistance to a much smaller load resistance. That is as a unity gain voltage buffer amplifier.